So welcome everyone. In this talk, I will briefly show you how you can integrate iOS UI elements into Compose UI. But first, I will talk about our experiences in Kotlin and Compose Multiplatform. Then I will explore how to use iOS platform and its ecosystem to our advantage. And we will walk through an example using Lottie. And finally, I will cover some advanced integration techniques as well. So at Supercharge, we have been working with Kotlin Multiplatform for several years now. Our first project started 3 years ago. And we successfully shipped multiple applications, SDKs, and white label solutions since then. Our latest publicly available application is the GLS mobile application, where the UI is in Compose and SwiftUI, and the rest is shared between the platforms. Our experience with Compose goes back even further. We started using it since its first stable release. So it was natural to us to include in our portfolio the Compose Multiplatform as well. We started experimenting with it 2 years ago. We created multiple POCs since then with our existing Compose applications. And we started using it after the accessibility support arrived in the iOS side. We're currently developing 2 projects in it. One of them successfully passed the UAT phase. The second one is still in development. JetBrains did a great job porting Compose to iOS. We only had a few minor issues with it, no blockers at all. It was very easy to use. It was like writing a simple Android application. The key challenge we faced was that not every Compose library is available multi-platform yet, but fortunately, integrating the native iOS libraries is relatively easy and straightforward, and there is just a minimal overhead, performance overhead when done correctly. If to fill the gap of the missing functionality, iOS provides many built-in capabilities that often require third-party dependency on Android. These platform libraries can be used directly from Kotlin without any additional setup. For example, for scanning QR codes, we could use AV Foundation framework for image processing and camera preview inside Compose. And for QR code image generation, we could use Core Image and Core Graphics. Similarly, for maps, we could use Apple's MapKit. It provides everything that we needed for the map. And you can read about the MapKit integration on Medium. I wrote 2 articles about this. So it goes into details how to do it, how to manage memory, and so on. If the iOS platform does not provide what you need, you can fall back to the iOS ecosystem. It's a very mature ecosystem. It provides anything you want. Everything is implemented now. For dependency management, iOS offers 3 solutions. Each has its pros and cons. The CocoaPods is the oldest of them, but it will reach its end of life next year. It is used by React Native and Flutter under the hood, both of them working on replacing CocoaPods with Swift Package Manager. CocoaPod supports dependencies as source code or precompiled binary frameworks. It has a Gradle plugin, which simplifies the integration with Kotlin, and it generates the interop definitions for you. The second one is cartridge. It requires more initial setup, but it provides you more control how you manage your dependencies. It supports both source and binary dependencies, and it can precompile the source dependencies into a binary, which can reduce the project's compile time significantly. The drawback is that interop definitions must be created and maintained manually. The third option is the Swift Package Manager. It's the official dependency management from Apple. It supports both source and binary dependencies, but it can't precompile them. It makes linking with Kotlin a little bit trickier if you don't have a binary and only the source code. Similar, the cartridge interop definition must be created manually. For our example, I'll choose Lottie. It's a simple animation library that is available for web, for Android, for iOS. On Android, a Compose library is available, but I checked the source code, and they depend on the Android view system, so no multi-platform support from them in the foreseeable future. But an official wrapper library exists called Kotti. It's a perfect example because it's small and easy to integrate. Before we can access the Lottie code in our code base, first we need to create a definition file for generating the Kotlin bindings. You can specify here the language used by the framework. The default is C, so we set it to Objective-C. You can also tell the compiler which modules you want to use. Lottie has only one module, but for example, Firebase has some frameworks that contains multiple modules. And you can also set some linker options here as well. Next, in your build Gradle, you must create a new C-interop definition. It must be defined for all targets. Here you can see it's for RM64, but it must be declared for iOS simulator and X86 as well. Here you can set the definition file's path. Also, you can tell the compiler where it can find the actual framework during compile time and during runtime. We can also set some additional compiler flags if needed. Lottie needs these F modules for some reason. After we have the definition file set up, during Gradle sync, it will generate all the Kotlin bindings for us, and we can access it from our common or from our Kotlin code. Next, we must define a common API that we can use from the shared code. You can design this API to suit your own needs, or create one that mirrors the Android API for consistency. In our example, I will follow the Android API to make it more familiar. In the common code, we are defining a composable Lottie animation function and related components. And with the expect actual pattern here, we will provide the implementation for Android and iOS into different sources. The Lottie composition interface will hold the animation view. The remember Lottie composition will load the Lottie file into the composition, and the Lottie animation composable function will render the animation for us. On the Android implementation is pretty straightforward. The Lottie composition is just a type alias. And remember, Lottie composition has some loading. It loads the file with the compose resources common interface and calls the underlying library. And in the Lottie animation is basically just a delegate to the underlying library. On iOS, Lottie is a Swift library. Kotlin can interop with Swift properly yet. JetBrains working on it right now. Some preview is already available, but for this example, we use the Objective-C compatibility. Lottie provides a compatible animation view that is basically the Objective-C wrapper on top of the Swift library. Our interface implementation is just there to hold this compatible view. And to show you, I will show you how it is done on the Objective-C side. It's fortunately it's pretty easy to read, even if it's Objective-C. It loads the file into a byte array, which is represented as NS data on iOS. Then it will pass the data to the constructor of the compatible animation view. And after the view is created, we will call some property setters to set some sizing and scaling on it. And here is the Kotlin equivalent. I omitted some compose boilerplate so we can focus on the implementation. And as you can see, it closely mirrors the Objective-C implementation. The only difference is that we load the data differently. First, we load the file into a byte array and convert the byte array into an NS data. The rest is basically the same. Before we start using this animation view, we must first familiarize with the UIKit view, which is the iOS equivalent of the Android view composable function. It provides the same functionality. It allows to embed UIKit components into our compose UI. It provides the same callbacks, and on top of that, it provides some additional callbacks to clean up the memory if needed. In the factory method, the compose animation view depends on the compose state, so we can't use it in the factory. So we use a UI view here, an empty UI view. It will serve as a host to our animation view. And we also can set some properties on it that don't depend on the state. But before we see the update callback, here is the Objective-C implementation of the code we will transform to Kotlin. Here we add the animation view to the host view, then set some constraint on it so the animation view has the same size as the host view, and then we start animation on it. And here is the update callback. It's, as before, it's basically the same, but with Kotlin syntax. First, we retrieve the animation view from the state, then add it to the host view, set some constraints, and start the animation. For more complex scenarios, or when you want to use a Swift-only library that does not provide an Objective-C compatibility, you can use the Compose Swift Bridge library developed by TouchLab. It is built on top of their SKI and Kotlin symbol processing. It generates all the boilerplate needed to provide the actual implementation in Swift. It's a pretty cool technology and pretty new. So it's still experimental, and it adds some complexity to the build configuration. So it should be used only when no other solution is available. And using the same Lottie example, we only need a single Lottie animation composable function this time. We must mark the animation with an Xbox Swift annotation. This will tell the plugin to generate the boilerplate for us. Next, we must update the entry point for our compose application. The native view factory is provided by the bridge, and we will implement it in Swift. The UI implementation is just a regular Swift UI view, nothing fancy here. The bridge also generates an observable object for all the parameters at the composable function. This way, the Swift UI view can always stay up to date with the composable state. You can use the observable object in the view directly, or use a binding class like this. This will receive the state and render our view. Finally, we implement the view factory, where we pass the observable to the binding, and we pass the binding to our main entry point. And basically, that's it from me. A more detailed guide is in my Medium blog post. Thank you for your attention. And you can